In this chapter, the researcher will discuss the design flowchart, block diagrams, and circuits that will be used to obtain the specified goals of this study. All the circuit design and layout will be done using HPICE. So here the researcher create flowchart for the methodology. So first, we have the planning of desired specifications. Next is designing the architecture. After the designing of the architecture, we will be conducting pre-simulation, and after that, is the design specification met should be the questions to be considered. So if yes, so we will proceed in making the manual training guide. And so here are the parameters or the considerations that we had to consider in designing the methodology. So first is the operating circuit at the subthreshold voltages. So operating at the subthreshold level means that no voltage in the integrated chip IC rises above the threshold voltage. Operating circuits and supplies below 0.9 volts enables a circuit to have very low power consumption, provide subthreshold currents. And another one to consider is the MOSFET aspect ratio for the subthreshold operation, because it entails that a higher aspect ratio increases the current gain and subsequently a higher current for a given voltage. The same is for a higher M. That means the multiplier times the aspect ratio. And of course, we will take into consideration the nano micro 0.18 micrometer and the 65 nanometer process technology on HPI simulations. So as the technology progresses in small dimensions and lower power supplies, the matching dominated circuits are expected to see a reduction in power dissipation, whereas noise dominated circuits will see an increase. Shown in figure 3.5 is a BJT-based temperature sensor. A transistor is biased by current source, and the voltage between its base and emitter is given by VBE is equal to KTQLNICIS. This is a complementary to absolute temperature CTAD, where K is the Boltzmann constant, T is the absolute temperature, and Q is the electron charge, which is strongly process dependent. Obviously here, as we can see, VB is a nonlinear function of temperature. Furthermore, process spread may cause large errors in the due variations in IZ and IS. Therefore, BB is not suitable as sensing signal. To emulate the process error, the base of two transistors are connected together. Another consideration that we should take into account is the peak voltage, because the difference between the two VBE is given by the change of the VBE is equal to VBE2 minus VBE1. So as a result, the process-dependent IS is cancelled out. Ideally, the change of VBE is proportional to absolute temperature or the positive or the PTAT. And of course, PTAT, a diode at the in here in this figure, resistor in series with the is also we take into account, because in a diode D, which may comprise of diode connected transistor, is in series with R, is forward bias in response to current I to provide a CTAT voltage V. Taking the output voltage V from node A provides a sum of the CTAT and PTAT voltages, reducing the value of R appropriately. And of course, here for our methodology, we also include the analyzing theory and simulating of the conventional bandgap voltage reference in order to further understand the workings of the conventional bandgap. So here at 3.5.1, we have a generating negative DC voltage. As shown from this equation, it gives a temperature coefficient of the base emitter voltage at the given temperature T, revealing dependence on the magnitude of VBA itself. And also in this section, 3.5, 3.5.2, um, it is um, it is how we generate a peak voltage. Thus, we can see that DBE exhibits a positive temperature coefficients, right? So, is we can see in this architecture, um, this is the architecture that simply generates the peak voltage of our given circuit. So, after those considerations, we finally finalize the generation of the analyzed concept for those theories. So this is a generation shown in figure 3.5.1 is a generation of the band gap voltage reference using the analyzed concept discussed earlier. So it is the also we also tried to simulate the conventional band gap in order for us to see if it's working. So here is the results of the simulation test. So we have a process technology in a zero point 0.1 micrometer at the supply voltage 1.8, and the result shows that we obtain a TC of zero point 0.6 ppn, sensitivity to VDD which is very small, around 0.030%, max VRF of 1.2327 and the minimal VRF of 1.2325. So it just shows the working that the band that we are simulating is working properly. So here we will proceed to the block diagram of the proposed circuit architecture. So basically our proposed architecture for the band gap is consists of three